Hi guys, and welcome to the last video in the Motion and Energy series for Year 10. This one focusing on collisions, and we'll just pull some of the main ideas together in this one. So a little bit on collisions, a little bit on car safety devices um, associated with potential damage from collisions, and then just a very small final comment on some of the sports stuff, just to wrap the topic up. So first of all, we need to look at the fact that there are two types of collisions that we can describe in physics, and those are elastic collisions and inelastic collisions. In an elastic collision, both momentum, which is a new concept we haven't really talked much about, and kinetic energy are conserved. But in an inelastic collision, only momentum is conserved. Now, momentum is a concept that's, I guess, related a little bit to inertia. It's probably the closest thing we can look at. Momentum is equal to mass times velocity. So momentum is what objects have when they are moving, and they have more momentum if they are moving quicker or if they are more massive. The problem that we have with different types of collisions is that momentum is always conserved. So that means that we either need to look at what happens when two objects meet head on, what happens to each of those objects as a result of that collision, and we need to look at it for each individual component. So if, for example, a car hits a wall and bits of the car break off in different directions, we need to take account of all of those if we're going to look at conservation of momentum. Now that's really a little bit beyond the scope of a Year 10 physics course, something that's more likely to, that you're more likely to deal with later on. So for now, we'll just introduce these concepts and the fact that most of the collisions that we look at are inelastic collisions. And that's because almost always heat and sound, you can hear a collision and certainly some heat generated when two surfaces come into contact. Both mean that the kinetic energy before the collision is not the same as the kinetic energy after the collision. So for an elastic, rho before must be equal to rho after, and kinetic energy before must equal to kinetic energy after. But for inelastic collisions, rho before is equal to rho after, but kinetic energy before is not equal to kinetic energy after. Okay, the closest example of a elastic collision would be something like billiard balls. A lot of that energy is transferred to the next ball or the Newton's cradles. But again, there's still a small surface in contact, so you get heat and you can hear them hitting each other. So then you're also getting sound. Now, associated with the idea of collisions is another very important physics concept called work. Now, the interesting thing about work is you actually have to move an object in order to do work on it. So if you're leaning against a wall and pushing it as hard as you can, you may end up straining your muscles and feeling like you've done a lot of work. But in a physics context, the concept of work only applies when a force is used to move an object. And therefore, in order to calculate work, we need to use the formula work is equal to force times distance. So obviously, if the distance is 0, then anything multiplied by 0 is going to be 0, and therefore we're going to end up with no joules of work. Now, work is a scalar quantity like energy. And in fact, as I mentioned, if the object doesn't move, then there is no work done on it. And what often happens as a consequence of us doing work on an object is that it changes its kinetic energy. We can sometimes have work being done by an object. Often when we've put some work in to, say, raise an object up in a gravitational field that has gravitational potential energy, that can then be transferred into kinetic energy, which can do work as the object is falling. And that's some of the principle around what you did with your Rube Goldberg machines, is you're actually using dominoes and marbles and things like that to actually do work on other objects and keep your machine going. So the probable main point of this whole topic was really about the application of the study of motion to real life situations. So we looked at two situations in particular where motion is really important. One is in sport, when we're trying to maximize our sporting performance, work out angles, forces, velocities, how we can get balls to move or to dip or to change their direction and make sure they go in a certain direction that we want them to go in. And same thing with ourselves if we're running, how we can maximize our performance, increase our takeoff forces, rapid accelerations, and keep those maximum velocities as long as possible. But the other situation is in car safety. Obviously, there's a lot of car crashes. We get advertisements all the time for car insurance, and that's because things happen to cars. And a lot of the technology that's gone into automobiles from manufacturers has gone into making cars safer, so that in the event of a collision, that the occupants are protected as well as they possibly can be. Now, any car that's moving must possess kinetic energy, because you'll remember kinetic energy is equal to a half mv squared. And so therefore, if the object's moving, it must have kinetic energy. If it strikes a wall and the wall is not moving, the kinetic energy is converted into heat, it's converted into sound, we can hear it, sometimes there may be lights, sparks. You may find that pieces of the car may break off, they will continue to move. And also the car may distort. As it crumples, it may distort. And in fact, as it distorts, that may give it some elastic potential energy, and often it can then bounce off the wall as that elastic potential energy is converted back into kinetic energy. But generally speaking, it won't bounce back with the same amount of energy that it had before it hit the wall. So a lot of that energy is being dissipated or released or transformed, probably a better word, into other forms of energy. Not a very efficient type of collision, this one, and certainly, definitely an inelastic collision, as so many so many other types of energy are actually being converted in this particular collision. In addition to what's happening to the car, the people inside will also experience a force as their speed decreases to 0. So obviously that's going to be very different if we're going from 60 kilometers an hour to 0 than if we're going from 100 kilometers per hour to 0. So either of these two situations is obviously going to happen fairly instantaneously, and that's going to create some very large forces on the car and also on its occupants. So what we want to try and do is seek to do two things effectively, is to spread that force over a longer distance, so we increase stoppage time, and say the ABS braking system is one of the ways of doing that. It rather than putting the car into a skid, it grips on and off, and so therefore you get a little bit more control of the car as you're sort of seeking to stop, and then it's trying to give you that little bit of extra time to either A, avoid a potential collision, or B, maximize the amount of time and stopping distance. So we've got to try and increase stoppage time or increase stoppage distance. And most of the devices that we see in cars are designed to do one or both of those things. So let's have just a look at a quick look at a couple of those. The seat belts have been around for some time now, and the idea of the seat belt is again to slow your progress towards the steering wheel or the dashboard, so that the seat belt is going to actually put a force on you that's going to slow you down so you don't hit that as quickly. Not going to do very much to the stopping distance, because you're still going to probably go forward into the dashboard or into the steering wheel, but it is going to just slow you down a little bit and therefore increase the time. So slower progress is an increase in time, and that's going to result in a decrease in the force. The same is true of airbags. Airbags are designed to act as a cushion which again is going to increase the time and therefore decrease the force. Crumple zones actually start to dissipate some of the energy through the car before it's transmitted to the occupants of the car. So the crumple zones are again an issue of trying to increase, in this case, the time and decrease the forces that are going to transmit it to the passengers. So the main thing we're after is to increase the stopping distance, to increase the time for that deceleration from, say, 60 kilometers per hour to 0. In doing that, we reduce the net force because what we're looking at is acceleration is equal to V minus U on T. That's one of our important equations. And because at the beginning, before the collision's about, you have a certain speed. After the collision, we'll assume that you're going to come to a stop. So the top for any collision are going to be set. They're not always going to be the same if you're traveling at different speeds, but they're going to be set. So therefore, in order for us to have a small acceleration, and we know that because F equals ma, and you can't change your mass, if acceleration is smaller, then the force that you experience will be smaller. Therefore, we have to have an increase in T. And that is how this whole area of safety devices works. The whole point is that we're trying to increase the time in order to decrease the acceleration and therefore decrease the force that acts on us, hopefully minimizing personal damage, personal injury. Now, collisions also occur in sport, and it's interesting to have a look at different types of sports and the way in which these collisions can occur. So if I just change the color for a second, you'll notice here that we have a golf ball that is stationary, so its velocity would be equal to 0. And the club head is coming through. Now the club head has been lifted, so it's going to have some gravitational potential energy at the top, and that's going to be transferred into kinetic energy down the bottom, just as it strikes. You'll notice here that there's a level of distortion as the club head strikes the ball, and therefore there's going to be some elastic potential energy. Now that elastic potential energy is then going to be converted into kinetic energy as the ball starts to then move away from the club head. This is a very common situation that occurs. It occurs whenever bats are striking balls or rackets, but it also occurs when, for example, you're kicking a ball or even throwing a ball. There is a force that's applied. That force applies a certain amount of work to the object, to the ball mostly, and then that ball is given a certain amount of kinetic energy as it's moving, and then as it moves through the gravitational field, there's also going to be some transfers from kinetic energy into gravitational potential energy, and then back again to kinetic energy as it falls back to the ground. So we can also describe our collisions, our motion in any sorts of sports based on those very important equations of motion. You remember the 5 quantities that are important for us to be looking at are velocity, initial and final, acceleration, distance or displacement, and time. Our important equations are acceleration is final velocity minus initial velocity divided by time, and our Newton's second law equation is that force is equal to mass times acceleration. Using these important relationships, quantities and formulas, we can analyze most of the motion that you're going to be looking at and come up with some very important ways of both analyzing and describing the motion that we see. So let's just finish with a couple of questions then to take us out of this topic. Firstly, if a heavy object takes a force of 200 newtons to move at 3 meters, how much work is done? Well, we know work now is equal to force times distance. So therefore, the work is equal to 200 newtons times 3 meters, which is going to be 600 joules. So the amount of work done is 600 joules. In the second situation, which is more dangerous, falling from 10 meters above ground onto a mattress that is 0.2 meters thick, or stopping over 1 meter inside a car that crashes at 100 kilometers per hour. In order to do this, you're going to need to work through a few things, and I'm going to make one assumption. I'm going to partly do this question and leave it for you to actually ask me for the final solution. Let's assume that you have a mass of 50 kilograms in each of these situations. If you're falling, then you have gravitational potential energy equal to mgh, which is a mass of 50 times, let's round 9.8 up to 10, and the height is 10 meters. So you're going to have 5,000 joules of gravitational potential energy. Assuming minimal losses due to air resistance, that 5,000 joules of gravitational potential energy is going to be converted into kinetic energy just as you're about to hit the ground. So we're going to therefore have a force that's equal to the work, or the kinetic energy, divided by the distance. In this case, we've got 5,000 divided by 0.2, which is 25000 newtons. In the second situation, if you are in the car, you can calculate the kinetic energy, because kinetic energy is equal to 1/2 mv squared. But don't forget, you're going to have to convert your velocity from 100 kilometers per hour into a number of meters per second. Then we're going to square that number, multiply it by our assumed mass of 50 kilograms, and multiply it by 1/2, and then divide it by 1, because once again the force will be equal to the work done, or the kinetic energy, divided by the distance, which in this case is going to be 1 meter. Have a go at that, and I'll tell you the answer when you ask me the question. Thanks for watching.